All right, we're ready for chapter 2, lesson 6. You notice that we didn't do lesson 5, at least in the year. Well, at least the year I'm first making this video. I may go back and make a video for lesson 5 at some point, but it's because of my de-emphasis on the use of graphic calculators at this level, and so that's kind of why that is. But if you're just happening upon this video on YouTube randomly, then you probably aren't even using the same textbook that I am using to go through, and so you're just thinking, well, we skipped a number, but that's why. Anyway, we're going to be talking about special functions. These functions, we're going to talk in the next lesson about parent functions and some other different types of things. But these special functions are a few different types of functions that kind of build on linear functions. They're essentially linear functions, but with some added, a little bit of added stuff. The first type of function is a piecewise function. So a more complete way to say this would be a piecewise defined function, right? And so this you can define the same function without using a piecewise definition. This is just a easier way to look at it, and I don't know, I'm saying more words than are even necessary. But a typical piecewise function is something like this. Now, in the Algebra 2 video, we just have linear functions as pieces of the piecewise function. Later in pre-cal, we may see we may end up seeing more functions, and we may see things like quadratics in here or cubics or whatever. They don't have to be linear functions, but to get the point of what a piecewise is. So a piecewise function is a function that's defined in pieces. And so you kind of notice that they're look like this. We got function notation right here. And we have the definition of the function in this bracket. And this this function kind of has two different puzzle pieces. It's got the function parts. You'll notice that there's more than one. There's two in this example. And then the condition parts, right? And so the conditions are kind of what divides up our graph, our grid, into more than one place. So you notice that we're at around -1 for both of these. And so, especially when we're first doing this, I find it can be easier to kind of dot in some lines. Now, well, there's only one breakpoint here. In our next example, there's going to be two. But in here, to kind of dot in a grid line where the breakpoint is. So at x equals -1, we're just going to kind of dot in this thing, right? This is not an asymptote. If you learned about asymptotes, this is not defining that, but it's the same. Having this dotted line is kind of the same purpose, to kind of help us visualize a break. And so what is going on here in this piecewise function is we're going to use one definition on the left side and a different definition on the right side of this thing. And so let's kind of take a look at what this is going. So when x is less than -1, so we're talking about this side, we're going to use the definition x minus 2. And when it's greater than or equal to, we'll see what to do with that here in just a second. You might be able to guess it if you think about it real hard. But when it's greater than or equal to -1, we're going to use the definition x plus 3. Now these would both, like if I put y equals this and y equals that, then those are just linear functions, right? We'd go like to do this one, we'd go up 1, 2, 3, we'd put a dot, and then the slope is 1, so it's up 1 over 1, up 1 over 1, and then we connect the dots and graph in the line. Well, that's actually basically what we're going to do here. So that's, I mean, I made a mess of it, but that's basically what this line is going to look like. Now, it's going to look like that from here over, right? So it's easier to do this one because it includes the middle. Now, we're going to have to find kind of what to do with where to start this other side in a minute, but let's start with the easy one first. So this one, if we were to grab it, like I just said, we would start by going up to the y-intercept, and we would put a dot right there. Let's do a different color. Let's make this one yellow, and this one, this blue color is fine, right? So for this guy, even though they're all part of the same function, they're just defined in separate pieces. And we're going to see that this is a function, but I don't know. We'll keep going. So we're going to go up 1, 2, 3. and put a dot. And then we're going to count the slope. Remember, if there's nothing there, it's a 1. So the slope is 1 over 1, right? So you'd go up 1 over 1, up 1 over 1. Then you would grab your ruler and you would connect the dots. So that's the way this is going to work here. I bet we can do better than that. Let's go. And that's good enough, right? So it's going to do the same thing all the way down to here. But it's not going to continue past this because we're going to use a totally different definition on the left side. We're going to use this definition over there. Now, on this one, we need to go back and check. It's because we need to know, are we going to put a solid dot or a open dot? And we're going to go back just to our same old inequalities thing. So this is this definition right here. This is x plus 3, right? And so it's equals. So for this one, we're going to put a solid dot, right? Now, this other guy over here, it gets a little bit tricky because we, normally we would go down 2 and then we would count our slope, but the graph doesn't exist over here. Our graph doesn't exist over here. So none of this should exist, but this is kind of what that one looks like if it wasn't a piecewise function, right? It's actually a parallel line, but scooted down, right? So what are we to do? Well, we need to find out where this graph hits this point. So I'm going to kind of pull this out. So f of x equals x minus 2. So that's this top piece, but without it. Now, what we're going to do is we're going to figure out and we're going to evaluate this function at -1, at x equals -1 to figure out where it goes. So we're going to find f of -1. How did I get the -1? I got it from, that's our dotted line, right? That's where that came from. So that's what we're going to do there. So we're going to plug in a -1 and then we're going to solve. So we've got -1 minus 2, which is -3. So f of -1 is -3. So this function, this part of the function intersects our dividing line at -3, right? And so we're going to go down to 1, 2, 3, -3. Now this is where we've got an open circle, right? This is this one right here. So we've got an open circle at -3. And we're grabbing the same way. Now, it's the same. We're going to look at the slope, and we're going to count the slope. Since we're going to the left, we got to kind of count it backwards, right? We still have 1 over 1. We can't go up 1 over 1, so we're going to completely flip that around. So instead of going up, we're going to go down and back. See how we did both backwards? Instead of going up, we went down. Instead of going to the right, we went to the left. So we're flipping everything. It's the same number, right? Because -1 over -1 equals 1 over 1, right? If we flip both of the signs, it's the same thing, right? So that's what we're doing. So we're going down 1 and back 1, down 1 and back 1. And then we're going to connect that. And we're going to have that. So this right here, and we kind of erase this so we can see what we're seeing. I'm even going to erase these guys up here. So this picture where this function is split up into 2 parts and it has this sort of separated thing is a piecewise function. I said earlier, this is a function, even though you're like, okay, it's going to fail the vertical line test because it's going to, wait, it doesn't actually hit the same here because this one it's not including and this one it is. So this is still a function. So let's do another example, but kind of flipping the script a little bit. So this time what we want to do is we've got a piecewise function here and we're supposed to write the piecewise definition. So again, what I like to do is kind of put some dotted lines wherever we see these circles, essentially, wherever it changes. So there's one right here, which is at +1, right? So there's going to be something going on there. And then there's another one. So this one has 2 different breaks, 3 different pieces, 2 different breaks, right? So there's another one right here, which is at +2, right? So those are going to be our change points. So when we define this function, f of x equals, we're going to have 3 different pieces. 1, 2, 3. I'm going to change it to the colors. I made these different colors so that it's easier to see what's going on. So this one, this pink one, is to the left of 1. So it's when x is less than. Now we need to look and see, is it a solid circle or a open circle? It's an open circle. So it's when x is less than 1. This thing is going to happen. We're going to write what that thing is in a minute. Give us a second, right? And excuse me. And excuse me. And then the yellow one is when it's greater than 1. So this time we've got like it starts and it ends. So between 1 and so when x is between 1, including, it's a whole circle, and 2. So when x is between, so x is greater than 1 and less than 2. So we've got a compound inequality going on there, right? And then that's what's going to happen if you have a piece in the middle, right? And then this one is whenever x is greater than 2. So this purple one is when x is greater than or equal to 2. And it's equal to because it's filled in circle, right? So there's our conditions. There's where we're laid out. So let's go here and see if we can fill in the pieces of this. So this guy, so we've got to figure out, and basically what you do is you do just like we did in our last lesson. Was it the last one? I don't know. One of the previous lessons in this chapter where we're writing equations of lines, because we've got a picture of a line and we need to write that equation. So we need its y-intercept and we need its slope, right? And so the y-intercept is in a weird place. So we're going to have to find it in a minute. So we're going to do a little bit of extra work to get there. So let's take a little bit of work. Yay, we like that. So we're going to do this the same way we've done before. And we're going to find 2 places where this pink line crosses at a cross. It looks like it crosses at a cross right here, and it crosses at a cross right there. You could also pick this one, which might even be better, but we're going to pick those. So this point right here is -1, back 1, up 1. So -1, 1. And this one is -1, 2, 3, -3, and then down, so -1, 2. So -3, -2, right? So those we're going to, just like we did recently, we're going to write the equation of the line that passes through those 2 points, right? So we're going to find the slope of the line. So let's do that. So m equals y2 minus y1 over x2 minus x1. All right, so then we're going to plug it in. Here we go. And then there. So we're going to plug it in. So y2, let's pick this as the second point. Why not? So we're going to put in 1. And then for y1, it's -2. For x2, it's -1. x1 is -3. So then we're going to ka-chink, ka-chink both of those. Ka-chink, ka-chink, right? So 1 plus 2 is 3. And -1 plus 3 is 2. So the slope of this line is 3/2. So we've got y equals 3/2 x plus b. We need to figure out what the b is. So we're going to pick one of these points. I'll pick the one with just ones. Sounds good. So we're going to plug in for y. We're going to plug in +1. And for x, we're going to plug in -1 plus b. So 3/2 times 2 is -3/2 plus b equals 1. Then we're going to add 3/2 to both sides. Plus 3/2 plus 3/2. Those cancel. 1 plus 3/2 would be 5/2. Does that sound right to you? 2 plus 3 is 5. Yeah, 5/2. You can check it on your calculator or do the math yourself. Sounds good. All right, so b equals 5/2. So we have the puzzle pieces. We're going to go ahead and put the answer to this pink one. We're going to go ahead and put it up here where it belongs. So the slope was 3/2 x plus 5/2. So see, that's this first piece, this pink piece. We've got it set up right there. So we're going to do the same thing with the yellow one, right? We're going to have to pick two ones. Luckily for us, I don't know if you've noticed yet, but luckily for us, the purple one is really easy. We're not going to actually have to do any work for that one, but the yellow one we do. We're going to do the same thing. We're going to pick this point right here, which is 1, 1, and then this point right here, which is 1, 2 for the x, and then down 1, 2, 2, negative 2. All right, so let's find the slope there. The slope of the yellow one, this middle piece of the piecewise function, is going to be, I already wrote the formula, I erased it, so I'm just going to go ahead and start plugging in. You already have it on your page, I'm sure, because you're not likely to be erasing the notes when I do, because unless I've made a mistake, obviously. But, that makes sense. Okay, so we're going to plug in negative 2 as y2 and 1 as y1 and 2 as x2 and 1 as x1. So that equals, there's nothing to ka-chink, so negative 2 minus 1 is negative 3. 2 minus 1 is 1, so the slope of that one is negative 3. Okay, so we're going to do the same thing. We're going to pick a point, plug it in, plugging it into y equals mx plus b. Let's plug in the two ones. That sounds easy. 1 equals the slope of negative 3 times 1 and plus b. Multiply negative 3 times 1, which is negative 3. Bring down the 1, bring down the plus b. We're going to add 3 to both sides. So b equals 4. So now we've got the puzzle pieces. Let's stick it up here where it belongs. So, excuse me. So the slope was negative 3. So negative 3x plus b, so plus 4. No big deal. Now, I said that this one's easier. This one is a horizontal line, right? Horizontal lines would be an equation with y equals a number. Now, the y equals part is over here, right? That's the y equals part. So all we need to figure out is what it is. So if this function is greater than 2, if x is greater than 2, then it's always evaluates out to be 2. So that piece is that. So all of this together is the answer to that piecewise function. We've got a few more examples to do. The rest of them are a little bit shorter, so don't stress. Okay, so next one. So this is a specific type of piecewise function, and it's called a step function. And there are other types of step functions, but at this point, we're going to be focused on the greatest integer function. And the notation for it is like this, where we have these two double brackets. And these two double brackets are, what this means is basically, let me change colors. This is the integer, greatest integer, less than or equal to, x. So this parent function, we're going to learn more about what that means. This one right here is, so as we're plugging numbers in, so like if I put, let's say let's kind of make a mini table right here, just kind of a little bit of a mini one, and then we'll show how the pattern works. We're not going to go very far into this table, but if I plug in, let's say, and I'm going to, instead of putting integers like I normally do, I'm going to put on the x side, I'm going to put some random decimals. If I put 0.8, okay, so what will come out in the, I should stay consistent and instead write f of x here instead of y, right? So if x is 0.8, f of 0.8 here, it's going to be the biggest integer that's less than or equal to that, so 0. If I plug in 1.25, Greatest integer that's less than or equal to this number would be 1. And this would be if I put 1.87 or 8.82, because that's apparently what my pen wanted to write. That still gives us a 1. You see? And so that's what it does. Now, graphically, this is really simple. When we have this function, it looks like this. So it starts out right here, and if we plug in anything between 0 and 1, but not 1, then our answer is going to come out to be 0, right? And then if I put in anything 1 or greater, but not 2, so anything in between here, then it's going to be 1. If I plug in 2.6, 2.5, 2.8, 2.973654321, then it's going to come out as a 2. And so it's going to make this little pattern like this. It's going to make a stair-step pattern, hence the title step functions. Okay, so this is the parent function. It'd be the same thing here. If I put in negative of 0.875, then it would then what's less than that is negative 1, right? That's the integer less than that, because they're going backwards, right? And so it's going to make this pattern going this way. So that is the parent function that goes with this guy. So in practical terms, this one, it's useful to kind of, it's like, what would this be for? And so that's what this blue example is all about. So let's take a look at that. I'm going to erase this. You shouldn't erase yours. You should keep it and do a new one. So let's do this example. An automotive repair center charges $50 for any part of the first hour of labor and $35 for any part of each additional hour. Draw a graph of this situation. So what you got here is up to the first hour. So then we charge $50, right? And then after that, we add for each additional. So if we go up to 2 hours, we charge an extra $35. And that's it. So if we work an hour and 30 minutes, then we're going to get charged 50 plus the 35, which would be 85, right? And so this is a step function. So we need to do some labeling here, right? We need to label our axes. This one would actually be better done just in quadrant 1. Well, it is just in quadrant. It would be better done if I used a big picture of just quadrant 1, but we'll just draw it up here for the sake of easiness. So if we count by, let's say, 50s, so if this is 50, this is 100, this is 150, 200, etc., 250, right? So the first one, where this starts, is right here at 50. So from 0 hours to all the way up to 1 hour, we're going to charge this. Now we do need to label. I should label since those are changed. This is 1. This is 2, 3, 4, etc. This is cost, and this is time in hours, right? So after that, we only go up 35. So this would be 85, right? Oops. So 85. Between 1 hour and 2 hours, we get charged $85. And then after that, if we go past the 2 hour mark, we jump up to another $35. So 85 plus 35 is what, 110-ish, something? 20, because math. 120, so we'd go up here. And we could get more specific if we were to graph this, and we could label these. But it's going to be something along those lines, and we keep going with this step function. So that's how step functions work. We've got one more type of function. This one is even easier and even shorter. So absolute value functions. It's very common for math books and math courses to talk about absolute value functions in relation to regular linear functions before we kind of jump into parent functions and all of those things, because absolute value function is just kind of a bent linear function. So I've done a parent function. Again, we're going to talk about more about what that means in our next lesson. But we've got the parent function in pink, and then we're going to do an example in yellow. And this time, unlike the other time, I'm actually going to leave both so we can compare them and see what's going on, which is kind of a preview for next lesson. So the linear parent function, again, we'll see what that means soon. The linear parent function looks like this, right? This would be f of x, or, yeah, well, that's fine. Well, no, we've already got two different f of x. Let's do g of x. Why not? Equals x, right? It has a y-intercept of 0 and a slope of 1, up 1 over 1. So that's just a basic linear function. What does the absolute value do? Well, what does absolute value do? It takes and it turns anything you put into it positive. And so what's going to happen here is what it does is it takes everything that's negative and it flips it to be positive. And so that's exactly what it does. It just takes and it turns it this way. So it looks just like a V, right? So we're going to, as this last example in this lesson, we're going to graph this guy, which is a translation of a parent function. Again, that's next lesson. But to drive the point home really, really well, that no matter what it looks like, no matter how weird it is, you can still get a sense of what a function looks like if you'll just plot some points. And so that's what we're going to do with this guy. So let's make us a little t-chart and let's plug in some points, right? So let's do our old standby, -2, -1, 0, 1, 2. And if that doesn't get us a good picture, then we'll add some more and see where we go from there. So if we plug -2 in here, -2 times 2 is 4, negative 4. I should scratch paper on this because I'm going to lose the thread and write something wrong. So -2 times 2 is -4. Absolute value of -4 is +4. 4 minus 4 is 0. So this gives us a 0. If I plug a -1 in there, -1 times 2 is -2. Absolute value of -2 is +2. 2 minus 2 is, 2 minus 4 is -2. So we've got a -2 outcome here. Now let's plug in a 0 in here and see what happens. Plug in a 0. That one we can do in our head, certainly, because 0 is just going to make this cancel out. 0 minus 4 is, of course, -4. All right, let's go the other way. It's probably, because of the parent function, you may have already kind of figured out what's probably about to happen, but let's prove you right. All right, so we plug a 1 in there. What's 2 times 1? Well, it's 2. Absolute value of 2 is 2. 2 minus 4 is -2. Oh, look, it's matching. What do you think this one's going to be? I bet it's going to be 0, but let's double check. So I plug in a 2 in here. 2 times 2 is 4. Absolute value of 4 is still 4. 4 minus 4 is 0. Okay, I think we've got a pretty good picture of what this is going to look like. So let's plot these points. So -2, 0, -2, and 0. So that's right here. So -1, -2. That's right here. 0, -4. That's right there. And 1, -2 is right there. And 2, 0 is right there. And so this guy looks, did I do it? Yeah, I did. Okay, looks something like that. So this is, again, preview for next lesson, but these changes, it took the pink guy, it pulled it down, and it scorched it in. We'll talk more about that in the next lesson. We've been yammering away long enough in this lesson. There's a lot of puzzle pieces in this one. Let us know if you have any questions. You can comment below with any questions or anything like that. If you're one of my students, do your homework. I'll see you in class. Otherwise, we'll see you on YouTube. Bye-bye.